In this video, I'm going to be talking about how we can improve the accuracy of our estimates of the integral. Of course, we know if we go for a higher order approximation, then the accuracy can be improved, albeit at the cost of more computational effort. But let's look at some other smart ideas that are out there. Let's do this particular experiment. Let an integral of some function f of x be evaluated using 3 points. X0 is equal to 0 and x1 is equal to 0.5 and x2 is equal to 1 using Simpson's one-third rule. This is an idea that can be generalized. So basically assume that we have three data points x0, x1 and x2 at which we have f0, f1 and f2 to be the f of x values. So we have that data table with these 3 points. Just to fix ideas, we are saying 0, 0.5 and 1 to be those points. Here, the size of the step that we take or the step size is 0.5 as we know, right? So 0 to 0.5 and 0.5 to 1. So h is 0.5. Because this is the first thought experiment we are going to do, we are just going to refer to that h as h1. So h1 is 0.5. Let's say the integral that we compute has this value of I1. And the error, because it is Simpson's one-third rule, it is going to be of the order of h to the power of 4. And therefore, in this case, where h is equal to h1, the error is going to be of the order of h1 to the power of 4. We can call this as error 1. Now imagine you are finding out the integral of the same function between the same limits 0 to 1, but now you have the benefit of two other data points. We have a point at x is equal to 0.25 and we have an additional data point at x is equal to 0.75. So now we are working with 5 points overall: x0, x1, x2, x3 and x4, with x0 being 0, x1 being 0.25, x2 being 0.5, x3 being 0.75 and x4 being 1. You have the corresponding f values as well. So using these 5 points, we can construct two P2 polynomials for each of the intervals, right? The first interval is going to be from x0 to x2. So this is one integral. The second P2 is for this portion, which is going to be the second subdomain or the second interval. So here what we see is we are integrating between the same limits 0 to 1 using data available at 5 points, and you can see the step size here is 0.25, and let's say the integral evaluates to a value I2. So the error in the second case is going to be of the order of h2 to the power of 4. Because we are using P2 here, you also use P2 here, so that is no problem. To summarize, we are integrating some function f of x between 0 to 1. In one case, we are basing the integral based on only 3 data points. And therefore, h1 is 0.5. The value of the integral that we get by doing Simpson's one-third rule using these 3 data points is going to be a value I1. And we are just saying the error is of the order of h1 to the power of 4. In the second case, we are doing the same integral based on 5 data points. So h2 turns out to be 0.25. Let's say the integral computes to I2 and the error is of the order of h2 to the power of 4. Now we know I2 would be a better estimate than I1 of the integral that we are seeking, simply because I2 is based on finer grid size. You are having the benefit of 5 data points in the second case. In the first case, you have the benefit of only 3 data points. So with more data points, of course, your accuracy level improves. So I2 is more accurate than I1. Now the question is, can we use I1 and I2 to get a better estimate of the integral? Because we are after this integral. I'm solving this problem once with h is equal to 0.5 and I'm getting a value I1. I'm solving the same problem using half in this example of the step size used in case 1. the integral comes out to be I2. So I put in the extra effort, right, of calculating integral I1 with a coarse grid, and I've also computed the integral as I2 using the finer grid. Why would I have to do these two integrals? Isn't it not sufficient for us to just compute the integral using a finer grid and say, well, the best answer I can give is I2. Now the point is, since you have invested extra effort in finding out the integral at two different grid sizes, are we able to use those two values I1 and I2 to get a better estimate of this function? So that's the question we are seeking to address here. Please note the error with I1 is 16 times the error with I2. That means we are saying error 1 is equal to 16 times error 2, because error 1 is of the order of h1 to the power of 4. Error 2 is of the order of h2 to the power of 4. But we know h1 is twice h2. h1 is 0.5, h2 is 0.25. So h1 is twice h2. Therefore, E1 is going to be of the order of h1 to the power of 4, which means 2h2 to the power of 4, which will be order of 2 to the power of 4, h2 to the power of 4. So 2 to the power of 4 is 16, and I can pull it out. 16 order of h2 to the power of 4. But order of h2 to the power of 4 is nothing but e2. So I can say e1 is 16 e2. That is the basis of writing this. So this is a remark that we make, and we have just shown why that is true. Now error 1 is going to be the actual value of the integral, the unknown value, but the actual value of the integral minus our estimate using the coarse grid size using h1. So that is error 1. Error 2 is the actual value of the integral minus my estimated value of I2. That's the error when I solve the problem with a grid size of h2. And we have just established that error 1 is 16 times error 2. So this is error 1. This is 16 times error 2. And from this, I can get an expression for I as 16 I2 minus I1 divided by 15. Because when you rearrange this, you're going to get I minus I1 is equal to 16I minus 16I2. So if you bring this I onto the right hand side, so 16I minus I will be 16I2 minus I1. So you can work out the algebra to go from here to here. So we have got an estimate of I from I2 and I1. I will be an improved estimate of the integral rather than I1 or I2. So the extra effort you put by solving the problem at two different grid sizes has helped us to improve the accuracy of the integral. Now error 2 will be I minus I2. So from this I you can subtract I2, which will result in the error 2 being I2 minus I1 by 15. So in this process, what we have done is we have eliminated the order of h to the power of 4 error by doing this. I will now have an error of the order of h to the power of 6. We can show that. Now, what have we gained? I2 had an error of the size of h2 to the power of 4. I, which is a better estimate, can be shown to have an error of the order of h to the power of 6. You can find the proof in textbooks or at certain good internet sites, etc. It is not difficult for us to derive that and show that this would indeed be the order of error in this new estimate I. So we can express I as a function of f0, f1, f2, f3 and f4. How? What is I2? I2 is going to be equal to, if you apply Simpson's one-third rule, it is going to be h by 3 f0 plus 4f1 plus 2f2 plus 4f3 plus F4. This is I2. I1, to be completely right, I2 is going to be H2 by 3. So I1 is going to be H1 by 3 multiplied by F0 plus 4 F2 plus F4. And we know H2 is half of H1. With those adjustments being made, you can evaluate 16I2 by multiplying this by 16 and subtracting off I1 and dividing the whole thing by 15. So you would have got this I as a function of F0, F1, F2, F3 and F4. This is what leads to what is called the Newton-Cotes formulae, which you can find tabulated again in textbooks, internet sites and so on. But the idea is this. We know the form that the Simpson's rule takes, and I2 and I1 are based on Simpson's one-third rule. So we have expressions for I2 and I1 like this. You just take those expressions with the appropriate H values and then compute this. And the answer you get, I, which is a better estimate of the integral, will be a function of the 5 F values corresponding to x0, x1, x2, x3 and x4. So I will leave that as an exercise to you. If you try it and if you have any difficulties, please let me know. Now we can apply the same idea to trapezoidal rule, and then the expression we get there with a similar logic, right? H1 is the coarser grid and H2 is the finer grid, because H2 is H1 by 2. So H2 has half the step size as H1. So with that, if you evaluate the integral using trapezoid rule with a coarse grid size, you get I1 to be an estimate of the integral. If you evaluate the same integral with a finer grid size, that means with more data points, you are getting I2. Then using those two answers, you can get an improved answer I using exactly the same logic like we did for Simpson's rule. We will get this particular expression. A better estimate of the integral will be 4I2 minus I1 divided by 3. And then you can quantify the error by just saying error 2 is I minus I2. So you take this expression for I, you subtract I2 from it, you will get this expression. Now, you know trapezoidal rule has order of h to the power of 2 error. Now by doing this kind of a calculation for I, the error will be of the order of h to the power of 4. So by solving the problem twice with different grid sizes, and each of those estimates having an error of the order of h squared, we can use those results and a formula like this to get an estimate of the integral which has got an error only of the size of h to the power of 4. So we can get substantial reduction in the error by doing this. So the price we pay is you have to evaluate the integral twice. One at a coarse grid size and one at a finer grid size. And then you can make use of these ideas to get it to this form and you get a better estimate of the integral as I. Now, this is the idea. As always, I minus IH2, right? I could have called it as I2, but I'm just calling it I minus IH2. That is going to be the error E2. And I'm assuming that H2 is finer grid. So IH2 should be a better estimate of the integral than IH1. The second line here says that the true value of the integral minus the estimate of the integral evaluated using a step size of H1, that is going to be the error 1. Alright, and H1 is greater than H2 because H1 is coarse and H2 is finer grid. So the first two things are expressions for the error in terms of the true value of the integral and the estimates obtained with step sizes of H2 and H1 respectively. Now for trapezoid rule we know E2 is of the order of H2 squared. E1 is going to be of the order of H1 squared because error for trapezoidal rule is of the order of h squared. Therefore, using these two things, I can write E1 as h1 squared divided by h2 squared into E2. Since h1 is bigger than h2, h1 by h2 will be greater than 1. Therefore, h1 squared by h2 squared will be a number that's greater than 1. So E1 is larger than E2. And that is also very easily acceptable because E1 is the error with a coarser grid. So E1 is going to be larger than E2. E2 is going to be smaller. Now this one gives you exactly how E1 and E2 are related. So E1 is h1 squared by h2 squared times E2. Using the first expression here, I can write I as IH2 plus E2. Basically this minus IH2 goes to that side and becomes plus IH2. So IH2 plus E2 can be written as IH2 plus E2, right? E2 is H2 squared by H1 squared times E1. Alright, so from this expression, we can write E2 as H2 squared by H1 squared times E1. So IH2, H2 squared by H1 squared, E1. E1 is nothing but I minus IH1. That is E1 from here. So I can bring all the I terms to one side and leave IH2 and IH1 terms onto the other side. We already have a I here and we have H2 squared by H1 squared times I here. So when it goes to the left hand side, it will go as minus H2 squared by H1 squared I. So I can take the I common on the left hand side and I have I times 1 minus H2 squared by H1 squared. That's on the left hand side. On the right hand side, I have IH2 and then a minus sign, H2 squared by H1 squared multiplied by IH1. And at this stage, what I'm doing is I'm taking this expression and multiplying throughout by H1 squared. Whence I get this. And then I'm dividing all the terms by H2 squared. So I get this expression. And now this one I can add IH2 and I can also subtract IH2. That is what is underlined in green ink. So whatever expression is there, I'm adding IH2 and also subtracting IH2. So there should be no problem, right? We are not distorting anything. But what happens is it helps to recoup the right hand side as h1 squared by h2 squared minus 1 IH2 plus IH2 minus IH1. So that is what we get here. And therefore, I can divide throughout by h1 squared by h2 squared minus 1 to get this final expression. I is equal to IH2 plus 1 by h1 squared by h2 squared minus 1 times IH2 minus IH1. This is the expression for I, expressed in terms of IH2, IH1, H1 and H2. So this expression is also right, except that it is in a different form compared to this. So there is nothing wrong about this expression and writing I in a different way. Nothing wrong with that at all. I've just done some extra processing to put it into this particular form. Now H1 is typically taken to be twice that of H2. So in the first example, when we did Simpson's rule, we said H1 is 0.5 and H2 is 0.25. So a typical way in which we may solve a problem is where H1 is 2 times H2. Therefore, this ratio of H1 squared by H2 squared turns out to be 4. So what you get this is 1 by 3 because H1 squared by H2 squared is going to be 4. So 1 by 4 minus 1 is going to be 1 by 3. So I is going to be equal to IH2 plus 1/3 I of H2 minus I of H1. So if you want to just simplify it, IH2 I can write it as I2 plus 1 by 3 IH2 is again I2 minus IH1. IH1 I'll write it as I1. So that is what it is. And I can write it as 4I2 minus I1 divided by 3, which is exactly what is written here. So we have just shown that the estimates from trapezoidal rule can be improved by doing this. 4 times the integral value computed using a finer grid size minus the integral evaluated at a coarser grid size, with the relationship between fine and coarse grids to be 2. That's the ratio at which this expression holds. If H1 was 3 times H2, then this expression would be different. The idea will still be the same, but the expression would be different. So we have to understand that this is based on the fact that H2 is H1 by 2, or H1 is 2 times H2. Then you will get this expression. I'll stop this video here and I will have a concluding part where I will do a worked out example. Thank you for your time.